All right, welcome back, guys. So here we are for the mechanics set two free response questions from the AP Physics C mechanics exam for 2023. Hopefully you found the video for set one helpful. Let's go ahead and take a look at set two. Now we have two cars, and you guys might be able to tell set two and set one have very similar topics. So this should be a little bit quicker than it was for set one. But anyway, we got two cars here and a piece of foam. We do know that the two cars collide, so the foam is going to make contact with car B for 0.5 seconds, and then they will both the cars will separate and move with constant velocity. Now, being a collisions problem, this is going to make use of momentum somehow, in some way. Part A, we're given velocity as a function of time for part A, asked which features could be used to estimate displacement, much like we had in the previous one with the force position graph. This one is actually also going to be area, area between 0 and 0.5 seconds, and it's going to be area under the graph. Let me specify that. Area under the velocity time graph between 0 and 0.5 seconds. That should give you the displacement of cart A during the collision, because this is the entire time while the two cars were colliding with each other. Use the information from the graph to determine the speed of cart B at time 0.5 seconds. It is not 1 meter per second. That is the speed of cart A. We have to use conservation of momentum here to help us find the velocity of cart B after the collision. So we would say that the total momentum before is equal to the total momentum after. Now we're not going to necessarily know whether based on our equation, right? We're not necessarily going to know if cart A goes goes to the right or to the left. But if we do go back to the previous slide, right, a couple of things that we do know is we do know that the two cars are going to separate and move with constant velocities, right? And so in terms of kind of thinking about this, the thing that we would have to kind of figure out is which direction cart A is actually going to be going, right? Would it make sense for it to go to the left? Would it make sense for it to go to the right after the collision? And in terms of actually kind of thinking about this, I would say that it would probably make more sense for cart A to go to the left after the collision, because cart A is the one with less mass. If cart A were to go to the right after the collision, then I do believe that what would end up happening is that they would either have to be going the same speed, or cart A would have actually had to have passed through cart B. But let's go ahead and actually work it out and see what happens. So if we do say that cart A is going to the right, right, then in that case, what we get is 1,000 times 5 is equal to 2,000 VB, which is what we're looking for, right? Plus 1,000 times 1. We know that the speed of cart A after the collision is 1. What this would actually tell us is that VB is equal to 2. So in fact, in this case, it does actually work out that cart B is not going to be going through. And actually, now that I read the question, the graph actually does show velocity as a function of time, not speed for cart A as a function of time. That's important because positive velocity is to the right. So my equation is correct here, right? 1,000 times 1 plus 2,000 times VB is equal to 1,000 times 5, right? And that's going to mean that VB is indeed equal to 2 meters per second. So VB does actually end up higher than VA, right? The speed of cart B is going to be 2 meters per second, and both of them are actually going to be moving to the right. So that is actually something that happens. My apologies. I didn't read the question fully correctly. Now we're actually asked to sketch a smooth graph for the velocity. We would expect it to have a similar trend for cart B, and we would expect it to level off much like cart A's velocity levels off at 0.5 seconds as well. So it would look like the same shape, just with a little bit flatter slope due to cart B having double the mass. Good. Moving on to part B on the next page, right? We are asked to calculate the magnitude of the maximum net force. Well, you might think that you just take a derivative once and set it equal to zero, but keep in mind that maximum net force occurs when the derivative of acceleration and therefore the derivative of net force is equal to zero. So first, we can say that acceleration is equal to the derivative of velocity with respect to time, which, for the sake of speeding this up, I'm not actually going to multiply the numbers together, but it's 3 times 64 due to power rule times t squared minus 96t, right? 3 times 64, I don't actually know what that is in my head. I believe it's 192, but I could be wrong about that. So to figure out where the net force is actually a maximum or a minimum, I'm going to set dA dt equal to zero, because again, acceleration is related to net force. So that's going to give us 6 times 64 times t minus 96, all equal to zero. You do the math and you will get that t is 0.25 seconds, which actually happens to be halfway through the collision. Right, that's going to give us the time at which the net force is equal to zero. Now, to figure out that value of the net force, I would say that net force is equal to mass times the acceleration at 0.25 seconds. So that's going to be 3 times 64 times 0.25 squared, right? Whoops, I don't know why I did the caret top. It's just 0.25 squared minus 96 times 0.25. And you would multiply all of that by the mass, which is 1,000. Now, what actually ends up happening is you get a negative number out of this, right? So we would actually have to take the absolute value to get the magnitude. And what you would actually find is that that would give you 12,000 newtons then. Absolute value would be 12,000. The actual net force is negative 12,000, which makes sense because what you would actually expect is that you would expect that the force on car A is to the left, therefore negative. All right, well, this is a quadratic function. So what I would actually say is that if we're trying to actually sketch a graph of the net force on cart A as a function of time, it should be an upside down parabola. Again, upside down because this is magnitude here. The function we got is a positive parabola, but the forces would all be negative. So the reason again why it's an upside down parabola like this is simply because we're plotting magnitude now, and that would be 12,000 newtons then. Good. All right, and now we can go ahead and move on to the next page. You guys might hear some paper crinkling. That's because I've actually already solved these just to try to speed it up and give you guys the best experience. Right, so you're not sitting here for too long watching me do the questions. So good. Now we remove the foam, right? Repeat the experiment. And in the original collision, we know that the magnitude of the average net force is F1. And without the foam, the average net force is F2 on cart B. We do know that without the foam, it's a shorter duration of the collision and that everything ends and starts with the same velocity in both. That has to mean that with the foam, you have a lower force. And the reason why you have a lower force is pretty simple. Each car has the same change in momentum in both cases, right? If that's true, then because change in momentum is equal to force times time that the force is exerted for, a lower time implies that a larger force is needed. And there you go. That's question 1 of the set 2 Physics C 2023 for your response questions. Let's go ahead and move on to question 2. Question 2 seems difficult. It's a bunch of springs in parallel attached to a mass with block, a block of mass m, and basically what we have to do is much like we did in set 1, we have n of them, right? So the first thing we have to do is derive an expression for the period as a function of n. This one's actually not as difficult as it sounds. Keep in mind that when you have n springs such as are shown in the pictures, they're all going to exert their own spring force up. Therefore, you should expect for the period to be much like it is for a normal mass on a spring, 2m times the square root of mk. Because I put parentheses, I guess I'll just do it to the 1/2. That was unintentional. But now the total spring constant should just be equal to n times k, right? Where k is just the spring constant of one ideal spring. Because now again, it's basically like you have one giant spring because all of these springs are acting together. So that would be the equation for our period: 2 pi times the square root of of nk. Excuse me, 2 pi times square root of m over nk. Good. Moving on to the next page, right? The next page is actually not too bad. The next page just has one part. It tells us to sketch a graph for t as a function of n if n is greater than or equal to 1. So I'll go ahead and mark n is equal to 1 right there. And what you should find is an inverse square root function. Again, pretty difficult to draw with my tablet. I apologize about that, but it should be inverse square root. Good. Moving on to the next page, draw a best fit line. What you guys should find with your best fit line, I'm not going to actually go ahead and draw it here because but you know, it's not going to actually pass through the points. If I calculate the slope of my best fit line, I got a value of 11.67. The points that I used were 0.5 comma 6 and 0.8 comma 9.5. Those were the 2 points I used to calculate my slope. But just for the sake of time and because I don't think it really adds much for me to try to do it with my tablet, I'm not going to go ahead and show you that right now. All right, second part, right? The mass of the block is measured to be 1.5 and calculate K. So I can say that T is equal to 2 pi root m over nk, just like I had from the first part. I'm using that expression to help me out, and I want to try to solve that for K. Well, the graph is plotting t squared over inverse m, so t squared divided by 1 over n should give me the slope. Now that slope should equal on the other side 4 pi squared over 4 pi squared times m over k. Therefore, k should equal 4 pi squared mass divided by the slope. And if that's true, I should get a value plugging in mass and slope of 5.07 newtons per meter. All right, next part is another experimental error one, right? The value given by the manufacturer, the value given by the manufacturer is larger than the experimental value. So our experimental value is smaller. And in terms of kind of thinking about that, that would imply that if we have a smaller value of k, you have a larger slope. And if you have a larger slope, you would have to have a higher period. And so I believe that in this case, what I would say, and again, I'm not 100% sure on these, this is probably the part of the physics CFRQs that I'm weakest on. But I think that if the springs have mass, I do believe that that would actually cause our experimental value of the spring constant to be lower. Because if the springs have mass, this implies a lower acceleration, and therefore a larger period of oscillation. Since period is inversely related to k, right, we would therefore expect a lower experimental value of k, which is exactly what the question is saying that we should have. Again, I'm not entirely sure if my reasoning's correct, but this is probably the one that I'm most confident with in terms of a reason. So I'll go ahead and stretch it out so you guys can read that entire thing. Good. Feel free to pause if you need to finish reading that, but I'm going to go ahead and move on to the next page then. All right. So in the next page, what it's saying is now oh, and I actually never solved this part. Oops, I forgot about this one. All right, well, this is I'm actually going to be solving part D for the first time right here. I completely forgot about it. All right, so it's saying a student conducts a similar investigation now that you have a horizontal one. There's no friction, and you still have the same horizontal distance from equilibrium and release from rest in the same trial. And now what you're plotting is t squared versus n to the negative first. Would the slope for this new investigation be greater than, less than, or the same as the slope? I would actually say that this should be the same slope. And the easy reason for this is that period and spring constant, period mass and spring constant actually, right? I can include mass in there. are all, and I'm just going to type this out, are all independent of equilibrium distance. It is true it is true that the net force is going to change, right? And therefore the acceleration at different points will change. But keep in mind that when you add a mass onto vertical springs, you are going to go ahead and actually change the equilibrium position from if you have no mass on a vertical spring. That should not affect the period of oscillation. All right. When n is equal to 1, the maximum speed is found to be Vmax. When n increases, will Vmax increase, decrease, or stay the same? Right. What we can actually say in this case is that US is going to equal 1/2 times nk times x squared, and that should equal all of the kinetic energy at maximum, right? So m Vmax squared. What I would say in terms of thinking about this is that, well, we notice that if you increase n, you are going to increase the maximum velocity, right? So therefore, maximum velocity is proportional to root n. Sorry, I keep mixing up the letters. Maximum velocity is proportional to root n, right? Simple justification for it. Therefore, the maximum speed should increase. All right, that's it for question 2. Now we can go ahead and move on to question 3. Back to familiar territory for me. Question 3 seems complicated, but it's actually not too bad. The first thing that we're told is that we have to derive an expression for the rotational inertia of the three-blade system, given in terms of m, L of physical constants, and we do know the inertia through the center of mass for each blade. It's 1/18 m L squared. And so what I can actually say is that the inertia through the end is equal to the inertia through the center of mass plus m times d squared, which is L over 3 squared. And if you're not sure where this comes from, this is the parallel axis theorem, which is one of the most important equations for inertia. Definitely something to have memorized, right? If for those of you who are watching this video to prepare for your future AP Physics C exam, know the parallel axis theorem. It says that the inertia through any axis parallel to one about the center of mass is equal to the inertia through the center of mass plus m times the distance between the axes squared, which in this case is L over 3 squared. So what's that going to be? Well, that's going to give us 1 over 18 plus 1 over 9, all in parentheses, times ml squared, which gives us 1 over 6 ml squared. Now that's just for one blade, so the inertia of the system is going to equal 3 times that, because there's 3 blades. So it's just going to be 1/2 ml squared for the total inertia. Good. Now we can move on to the next page. And this question is honestly kind of interesting. It's kind of a nice question. I actually really like it. While the wind blows, the 3-blade system operates at a constant angular speed, and we need to calculate the time to complete 1 revolution. Well, we have an equation for that on our equation sheet, actually. It's just t is equal to 2 pi over omega. And so in that case, it's going to be 2 pi over 2.6, which gives me an answer of 2.42 seconds. Part C gives us the angular velocity as a function of time, and we are asked to calculate the energy dissipated from t is equal to 0 until the system comes to rest, which would actually be infinitely long, right? So the final energy is going to be 0. This is all kinetic energy because it's things rotating. So in terms of thinking about that too, what I would actually get is that the initial kinetic energy is going to be 1/2 I omega squared, and we are given the inertia for the system as 6.7 times 10 to the 6th. So that would give me, if I plug in my values, 3.35 times 10 to the 6th, right? That's 6.7 divided by 2 times 10 to the 6th for the inertia, 1/2 I times 2.6 squared. Omega naught, sorry. And that should give me a value of 1.13 times 10 to the 7th joules. Now that should actually also be the energy dissipated because you're dissipating all of your energy. Good. Moving on to the next page, derive an expression for the net torque. Well, we do know that torque is related to angular momentum, right? So torque is going to be dl dt, but note that the inertia is constant. So therefore, it's just going to be I times the derivative of angular velocity with respect to time. If you go ahead and take the derivative of the exponential, you will get negative b naught I system times omega naught e to the negative b naught t. Moving on to the next part for angular displacement, it's the opposite. You take the integral, right? Angular displacement is integral of angular velocity from 0 to t, right? Keep in mind that you have to do bounds here, right? Angular displacement requires bounds. If you don't do bounds, you are actually going to miss the initial position, right? You're going to miss the initial position here. Or, sorry, not the initial position, but the steady state. What happens when t goes to infinity? You're going to miss that one. So this is going to be negative omega naught over beta naught e to the negative beta naught t from 0 to t. Neither of these bounds actually evaluate to 0, right? When you actually evaluate and plug them both in, this is what you end up with as omega naught beta divided by beta naught 1 minus e to the negative beta naught t. Good. And that's your angular displacement as a function of time. Next one says that beta, it's the same system, but beta greater than beta naught. Just and plot angular speed as a function of time for the second system. Well, it should just decay faster. Starts at the same position, right? And oh goodness, this is bad. But it should be an exponential decay just with a faster rate. And it should still approach 0 just like the original function. And that's it. That's it for set 2 of the mechanics FRQs for the 2023 exam. Let me know how you think you did on it. And in addition to that, right, let me know, of course, if you disagree with anything that I've put here or if you found this video helpful as well. The next videos that we have are the E and M questions. I'm going to do set 1 first, and I'll do set 2 afterwards, just like with mechanics. So be sure to stick around for those. Keep an eye out for those videos. Thanks for watching, guys, and I'll see you on the next one. Take care, everyone.